revise for the block test. Most of you guys, your school would consider it to be block test. That is going to happen most likely after the June holidays. So it's also sort of like your mid-year revision, mid-year exam. Okay, so very quickly, just do a brief introduction of myself. My name is Pamela. I'm just Overmark H2 Physics tutor. So I've been tutoring for 11 years now, and I do group classes as well as crash courses. So later there will be details on the group tuition or the crash courses that you guys can sign up for if you need more help for your physics. Okay, now I think this is the most important thing that most of you guys are come here for, which is what are we going to be covering today for today's session. So just a quick introduction of today's content. What I'll be going through is basically the topics that most of you guys should have already covered in school. The first one being the units of measurements, whereby we will briefly revise our base units as well as what are the rules that we need when we go through uncertainties. And then after that, we will be continuing with kinematics, whereby we will go through the equations of motions, especially for those that are parabolic motions, projectile motion actually. Then we will go through dynamics, where we'll look at Newton's law of motions and how can we apply them into the principle of conservation of linear momentum. And lastly, forces, we'll look at upthrust as well as the principle of moments. Okay, so today's session is a little bit short because it's only 1.5 hours, so it's not possible for me to go through everything, but I hope at least you can pick up some of the main things that are required in these 4 topics. Okay, so we just quickly go through some of the tips that I have for you guys when you want to revise for physics. Now, it's very important for you to actually do your own revision, especially be more disciplined. And how I personally do revision is that after I revise every chapter, I will take a blank piece of A4 paper and I will just, without referring to my notes, write down all the key concepts, all the formulas, and if I can, decimals on that piece of A4 paper. And then after that, I will refer back to my notes to see what are the parts that I have been lacking, what are the parts I'm actually missing, and that's the portion of that specific topic that I know I need to strengthen on. So you guys can actually use this method as well. Okay, then the second tip that I have for you guys is to practice questions, because physics is not like, biology or a little bit of chemistry where memorizing is required. It's really a lot more like math, where you need to do a lot of practices, and the more practice you do, the better you are at. Okay, just expose yourself to as much questions as possible. And lastly, your answering technique. So before you do a question, always read through the entire questions first. Don't just read the first part or just look at the diagram and just start answering. Always read through the entire question, have a feel of what they are actually looking for, and then set out your own game plan very quickly in your head. Okay, so without further ado, let's just get started with today's topic. Okay, hopefully you guys can pick out some of the important things that you need to know for today's topic. So first things first, the tips and measure that I have for your units and measurements is number 1, know the differences between errors and uncertainties. Okay, I think you guys know what uncertainties are and what errors are, whereby in your syllabus, they have already mentioned that there are 2 types of error, mainly your systematic error as well as your random error, correct? Okay, then they introduce to you what are these 2 different error and how they affect your reading. Then they also introduce to you uncertainties, but know the differences between these 2. Errors are unidirectional, which means to say that errors can be added or subtracted. Pretty much like your 0 error, you can add 0 error or you can subtract your 0 error from your measurement. But for uncertainties wise, they are bidirectional, which means to say that we can only add uncertainties. And that's the reason why you see that when you do multiplication, division, addition, or subtraction of uncertainties, there is a lot of adding of uncertainties involved. Okay, there's an error here, change it to plus. Okay, so let's just revise very quickly for units and measurements. If let's say I have a physical quantity that is K, then my absolute uncertainty is delta K. Take note, absolute means just the value, but fractional uncertainty will be delta K over K. Okay, because fractional and percentage uncertainty is my fractional uncertainty times 100%. So understand the difference between these three, because sometimes they might give you a variation of this kind of uncertainty. Okay, then in combining uncertainty, the important thing we need to remember is how do we add uncertainties together. For example, when I have addition or subtraction of uncertainty or quantities, whereby C, my final quantity, is made up of two quantities A and B added up together, then my absolute uncertainty, combined uncertainty for C, is the addition of the absolute uncertainty of A and B. Okay, then if my combined quantity for C is the subtraction of two quantities A minus B, then my absolute uncertainty of C will be the absolute uncertainty A and B added up together. Okay, now for multiplication and division, if let's say C is made up of two quantities A and B multiplied together, then we don't use absolute uncertainty, we use fractional uncertainty already. So the fractional uncertainty of C would be the fractional uncertainty of A and B added together. Same for if let's say C is made up of A divided by B. Okay, we add up the fractional uncertainty of each individual quantity. Next, for scaling, what are scaling? Scaling is basically if C is made up of a multiple of A quantity, where K is a constant. For example, C is 5A. So if let's say C is equals to 5 times of A, then my absolute uncertainty, so take note, this is absolute uncertainty, will be 5 times the absolute uncertainty of A. Okay, and lastly, for powers, if C is made up of A to a specific power n, then to find the fractional uncertainty, we bring down the power n times the fractional uncertainty of A. Okay, so that's a very quick revision. Now, the most important thing I need you to remember is this. All your uncertainties at the end of the day, express them into one sig. Okay, then once you've expressed your uncertainty to one significant figure, your measured value, that means your quantity, put it as the same decimal place as your absolute uncertainty. Okay, so take note for that part. So let's take a look at the first practice question here. Now it says, when an object moves relative to a unit, the fluid exerts a retarding force on the object, and this drag force, which is F, is due to the viscosity of the fluid. Now, under non-turbulent conditions, the drag force on a sphere moving in a tube of a fluid is given by this. So this is the formula that they gave us, where R is the radius of a sphere, so it's a quantity. N here is the viscosity of the fluid, also a quantity. And V is the velocity of the sphere, which is also a quantity. Now, pi here is considered to be a constant. And since it's a constant, it doesn't have any units. Okay, so just take note, no units. Okay, same for 6 as well. 6 is also a constant, no units. So, show that the base unit of viscosity N is given to be this. So this is one type of question that they like to ask, whereby they want you to make everything onto the right-hand side such that you only have your viscosity on the left-hand side to find the units for N. Okay, so if we were to just shift things around, manipulate the equation, you can see that viscosity is equals to your force divided by 6 pi RV. Okay, but then since we are only looking at units here, that means we want to take away our constant. So the units of N will therefore be equals to the units of F divided by the units of RV only. Okay, so I'm taking away the constants because I know they do not have any units. Then now, the keyword is I need to express it into base units. So basically my base quantity. I know that R, which is radius, is a base quantity because it's similar to length. Okay, it has the units meter. Now then for velocity, It is not a base unit, but I know that velocity is similar to speed and its base unit is made up of distance divided by time. So in this case here, the base units of this velocity is meters per second squared. Okay, then my last one that I need to speed up is actually my force. So for force wise, we usually use the concept of mass times acceleration. Okay, because these two can be simplified into their base units very quickly. And in this case here, we know that mass is actually in terms, the unit wise is kg, acceleration is meters per second squared. Okay, then this would be equivalent to meters, which is your radius, and meters per second, which is your velocity. So then we just do a little bit of simplification. kg, cancel the meters, okay, then you will have per second, and then divide by meter, which is equals to kg per meter per second square. Sure. Okay, so this is how we show the base units of viscosity in this case here. Okay, don't worry if you don't have time to copy it down. Later I'll upload the annotated document up into the Telegram chat. Then you can copy down whatever you need as well. Okay, so next, part B. They give another scenario here. I have a sphere, diameter 2.0 plus minus 0.1. So this is actually my diameter, d, and then plus minus my uncertainty, delta d. It falls under non-turbulent conditions through a fluid of viscosity, this. So this is actually n plus minus delta n. Okay? Using a ruler and a stopwatch, a student measured the velocity through the liquid, and they give us to be v here, and estimates the percentage uncertainty. So see, that's why it's important for you to know what is the difference between absolute uncertainty, fractional uncertainty, and percentage uncertainty. So now it says that the percentage uncertainty for this measurement referring to that of the velocity is 5%, which means here delta V over V is equals to 0.05. I just changed it into my fractional uncertainty by dividing by 100. So then determine the drag force acting on the sphere. Show your answer with its uncertainty. So we have already known earlier on that my drag force is equals to 6, F equals to 6 pi nRV. So from here, first things first, I quickly calculate what is my drag force. So 6 times pi, n here is 0.13, R here is, now, I want you guys to pay attention for this type of question. They like to trick you by changing the units. cm, meter, meter. So always check your units to make sure that they are actually the same, coherent. Otherwise, your measurements will be way off. Okay? So for here, they gave us diameter. But for this formula, they want us to actually use the radius. So obviously, we will need to take my diameter divided by 2, correct? So in this case here, it will be 2.0 divided by 2. But I also need to divide by 100 because I'm actually changing it into meters. Okay? Okay, then after that, I will need to times my velocity, which is given as 2.7 meters. So this is equals to 0.06617 Newton. Now I leave my answer in a long 5 significant figure or 4 or 5 significant figures so that my answers at the end of the day will be more accurate. Try not to change this to 3 feet too quickly. Okay, we call this our working step. So leave as much decimal place as you want. My advice usually about 5. Okay, or 4 or 5 is enough. Okay, so once I find F, now my next job I need to do is to find delta F. But because all these are made up of products of quantities multiplied together, therefore I cannot use my absolute uncertainty. I will have to use my fractional uncertainty. And since they are all multiplied together, that means that their fractional uncertainty is a sum of each individual's absolute fractional uncertainty of all the individual quantities. Okay, now 6 pi is actually a constant, so we don't include it in our calculation for uncertainty. This will just be delta n over n plus delta r over r plus delta v over v. Okay? Now, so delta f, all I got to do is just fill in all the relevant values over 0.06617 plus 0.02 over 0.13 plus, now for delta r over r, I can actually put the same value as the diameter one without having to divide it. Because if let's say I were to calculate my uh, radius, I will divide my diameter by 2. But that also means that my uncertainty has to be divided by 2 as well. So technically the ratio will still remain the same. Okay? So we take 0.1 plus 0.2 over, now for velocity wise, it would be 0.05. I don't even need to divide because I am given the percentage and hence the fractional uncertainty straight. So just using a calculator, you have delta F to be equals to 0. This whole thing here is 0.254. Okay, and then to calculate my delta F, put it to 1/6, it will be 0.02. So this is the thing that I need you guys to pay attention. Always put your uncertainty into one significant figure. Okay? Okay, then once we are done with that, next we need to express our F in terms of my quantity as well as its uncertainty. So then I need to check what is the number of decimal place in my answer, my uncertainty here. And I realize my uncertainty is 2 decimal place, which means that my answer here needs to be changed into 2 decimal place. And therefore, it is 0.07 plus minus 0.02 Newton. Okay, so that will be my final answer. Okay, so that's how we calculate for uncertainty. Next, in order to improve the accuracy of F, so let's say they find that F is not accurate enough, we want to improve the accuracy of the drag force here. Okay, explain which one of the measurements should be improved. So how are we going to do that? Now, first things first, we're going to look at all their uncertainties. Okay, you have the uncertainty for force, you have the diameter, you have the uncertainty for your viscosity, and you have the uncertainty for your velocity. Okay, then what do we compare? In this case here, we're going to compare all their fractional uncertainty, okay, to find out which one should be improved. Now, for delta D over D, this is given as 0.1 over 2.0. Okay, and if we were to calculate the fractional uncertainty for this one here, we will get 0.05. Then we also learned that our velocity fractional uncertainty is 0.05. And then now, my viscosity fractional uncertainty, it will be 0.02 divided by 0.13, which is equals to 0.15. So then you realize, out of these 3 measurements, my viscosity actually has the highest fractional uncertainty. So if I want to improve any measurement, I will improve my viscosity. Understand? So that it is actually much more accurate since the fractional uncertainty is the highest. So for this one here, we're going to say measurement of N viscosity should be improved as it has the highest fractional uncertainty. Okay, so to answer this type of question, we use the fractional uncertainty to compare. Clear? Okay, so that was for units and measurements. It's actually a very quick introduction for a very quick revision for units and measurements and the possible types of questions that can come out. Now, the next thing we're going to move on is the tips for kinematics. So, for kinematics, right, it's actually a very straightforward topic because there is only 2 types of questions, or rather 2 types of scenario they can come up with. It's those with linear movement. Either I move linearly forward and backward, or I throw something up or it lands down. So this is what we call linear. Okay, so for linear motion like that, whereby the acceleration is uniform, because most of the time for linear motion, right, the acceleration is due to gravity, then we will use these three formulas. I know that there's four formulas, but we don't actually have to use the S equals to half U plus VT, because this one, right, we need the initial and the final velocity. And usually most of the case, you don't really have initial. You have the initial, you might not have the final. So most of the case, we're using these three equations more often. Then what happens when it becomes a parabolic motion? Then it's a non-linear motion. So parabolic can be I launch something from the ground, forming a parabola, or I throw something like that, okay, from the top of a building. So these are called what we call non-linear motion. And in non-linear motion, the first thing we do is to always resolve your vectors into the horizontal and the vertical motion, so that you are able to analyze horizontal and vertical motion separately. Okay, so if let's say it's horizontal motion, now take note, for this type of motion, if you guys still remember, there is no acceleration. Okay, because horizontally, the motion is not affected by acceleration or gravity. And as a result, when we do calculation for horizontal motion, we don't have to look at all the ones with AS or acceleration. And that's why the only formula I need would be my initial velocity is equals to my final velocity, and that my horizontal displacement is my initial velocity times the time taken for the entire journey. For vertical wise, for this velocity or this motion, they're actually affected by acceleration, okay, or gravity. And as such, when we actually calculate or use the equation, we need to take our acceleration into consideration. Okay, so these are the things that you need to take note of. Okay, then the second tip that I have for you guys, or second revision, is what happens if there is air resistance. So without air resistance, we will use these formulas to actually do it. But with air resistance, we cannot use those formulas anymore because acceleration is not a constant. So what happens then is that we will have to analyze how is my projectile motion being affected. So generally, if you look at the diagram here, you can see that if it's without air resistance, the motion is pretty parabolic and symmetrical about the turning point. However, with air resistance, it's slightly tilted to one side. And not only that, there are a few factors that are being affected. But before we go through that, you have to understand that as long as there's air resistance, your body will experience a drag force. And this drag force always moves in the direction opposite the motion. So, horizontally, because my object is moving in this direction forward, okay, therefore my drag force is backward. So how does this affect my horizontal components? The horizontal velocity will be reduced, okay, because now there is a drag force opposing motion, and the horizontal range is reduced. So that means the horizontal distance traveled by the object will be smaller as opposed to originally. Okay. Second, vertically, how does that vertical motion, how is it affected? So there we are splitting into two components, the flight up and flight down. Meaning to say that when my ball or my object is traveling up, how is it affected? You can see that when it's traveling up, this is the direction of motion. The direction of drag force is therefore acting downwards. And because the direction of drag force is in the same direction as your weight, so therefore your net acceleration is actually larger than your weight, your gravitational force. And because it's larger than your gravitational force, correct, A is greater than G, what happens is that it will take a shorter time to travel up. That means it will move up faster, and the maximum height reached will be lower. Okay. On the other hand, what happens when we are looking at flight down? Now at flight down, because I'm moving downwards, this is my direction of motion, my drag force opposes it, so it's moving up. And as such, it is in the opposite direction to that of weight, which is downwards, and therefore my magnitude of net acceleration would be smaller than my gravitational force. And as such, your speed, final vertical speed, will become smaller than your initial vertical speed, because right now there's a drag force opposing it. Therefore, as my speed is smaller, the distance is sort of the same. The time to travel down is therefore faster. Okay? Then, so if they ask you to draw, this is the diagram we draw for if there is air resistance. Okay, so that was the brief revision of kinematics. Now moving on to the next one, which is for dynamics. Now for dynamics wise, I actually included it before revising for kinematics, is because I realized most of the time some of the schools like to actually put dynamics and kinematics question together, which means they like to actually fuse these two types of questions and then ask you. So we revise dynamic first before looking at a question. Now, the first tip I have for dynamic is very, very important. As long as you have a dynamic question, straight away, quickly draw a free body diagram if possible. Because once you analyze what type of forces is acting on the object, you can then very quickly find your net force. Because finding your net force allows you to then determine what are the forces to minus each other and what are the forces that cause the resultant motion. Okay, so always draw the free body diagram, and on top of that, indicate which direction you want it to be positive. This is very important, especially if, let's say, the question did not state. Okay, then once you have done that, if it is possible for you to actually find out the direction of acceleration, please find it and label it. Why? Because direction of acceleration actually gives you the direction of the resultant force. And once you know the direction of the resultant force, you are able to actually find out how the forces interact with each other. Okay, so for example here, one type of questions that is frequently tested is the type whereby I have a combined system of two different objects being placed together, or maybe they are held together by a string. Okay, then there is a force pushing them or pulling them. For this kind of question, how do we draw the free body diagram? So first things first, we will always have to understand that a combined system like this, let's say this is mass M and this is 3M, okay, I can actually combine them into just a body system like that with a box here, total mass to be 4M. Okay, and then once I get the total mass to be 4M, with the force pushing here P, I can then calculate my acceleration. Because if you look at this whole diagram as a whole, you realize the net force is just equals to my force P. And since net force is equals to MA, that means to say that my acceleration is P divided by my mass, which is equals to 4M. Okay, so therefore I get my acceleration to be P equals divided by 4M. Then from there, my whole force, my whole system has an acceleration in towards the right that is equivalent to P divided by 4M. And since I know my acceleration is acting in that direction, my net force is also acting in that direction. Okay, so that's how you actually find out the forces acting on this object. Then what are the other forces? The other forces would be, now here I would have a weight that is acting downwards in the middle. So this is my weight. And since it's on the surface, I will have a normal contact force acting upward as well. Okay? Okay, so that's for the whole system as a whole. Now, then for this type of questions, what they like to do is, or what you should do is, you should then isolate the system. Okay, so learn how to draw free body diagrams for not just isolated system, but also system as a whole. Okay, and the reason is because usually for systems as a whole and isolated systems, right, they will have a physical quantity that is constant. In this case here, acceleration is the one that is constant. So if we were to isolate the system out, so let's say this is for X. Okay, now for X wise, what are the forces acting on X? You realize that X has P that is acting in this direction here, and Not only that, it has force Y exerts on X, acting towards the left. Okay, so that's how we draw the free body diagram. And then on top of that, you have the weight of X that is acting downwards, so weight of X. And then if it's on the surface, there is a normal contact force, which usually tallies with the weight, so they would balance each other out. Okay, then since we know that the acceleration is acting in this direction, that means for this diagram, the net force is also acting in this direction. And therefore, what is my net force equivalent to? My net force in this case here is P minus F that Y exerts on X. Okay? Then relate it to the acceleration, which is the same acceleration as the whole system, P divided by 4m. Okay? Then now, if we were to draw for Y, same thing. For system Y, yeah, now you realize that system Y, there is no P acting on it. Why? Because P only acts on X. So for Y, there is only one force that is acting on Y, which is towards the right, the force that X exerts on Y due to the Newton's third law and the normal contact and the contact forces here. Okay. Then on top of that, there is the weight force that is acting on Y and the normal contact force due to the surface, which balance each other out. So we know that acceleration is also acting in this direction here, and it's given the same value as that of a system as a whole. Therefore, my net force is also acting in this direction here, F net. And based on the free body diagram of the isolated system of Y alone, it will just be equivalent to Fx on Y. Okay, so that's how we actually analyze diagrams like this. Clear? Okay, now the second tip that I have for dynamics is basically the one for resultant force. We know that for Newton's second law, F net is equals to ma. So usually what I like to do is I don't write F equals to ma, I write F net. So it reminds you that you are looking for the resultant force, not just any single force alone. And if we were to combine all the things that you have learned together, based on Newton's second law, resultant force is equals to the rate of change of momentum. So net force is equals to rate of change of momentum. Rate means divided by delta t. Momentum is mass times velocity. And if mass is constant, okay, that means it's not the case for a rocket launching into space where the mass is always different. For other scenarios, mass is constant. Then it's just delta v over delta t, which gives me my acceleration. Hence, F equals to ma. Clear? So take note, if they ask you to quote Newton's second law, don't say F equals to ma, because that is not Newton's second law. Newton's second law is F equals to the resultant force equals to the rate of change of momentum. Okay, and that the direction of my acceleration gives you the same direction of my net force. Then second, your change in momentum is the same as impulse. So change in momentum, which is actually final momentum minus initial. Actually, for any change you see, right, it's always final minus initial. Okay, then whether is it positive or negative depend on what your final and your initial are, will therefore be equals to your impulse. So it is equals to impulse whereby it's force times average force times the time interval if your force is constant. Okay, then we use F times delta t. But if let's say if force is varying, that means your force is not constant, then we have to use area under the Ft graph. Okay, so usually they will give you a Ft graph, then you find the area, they will give you the impulse. Okay, that's for tip number 2. Now for tip number 3, when we look at collisions question, sometimes they actually want you to do simultaneous equations. So explore the possibility of solving simultaneous equations when you have collision question, especially momentum question. And if you have simultaneous equation, use your GDC to solve, or your GC. Don't calculate manually, it takes a lot of time. You can use your GC in physics exam. Okay, so there are mainly 2 types of collision, elastic or inelastic. And no matter what collision it is, momentum is always constant. Okay, It's just that your kinetic energy is the one that changes. So since total momentum is conserved, we will always use the formula m1u1 plus m2u2 equals to m1v1 plus m2v2. That's it. Now take note, in this question here, direction matters. So therefore, you need to set who is positive, who is negative. Okay? Then this is for total momentum conservation. If in elastic collision, the kinetic energy is conserved, so then you can use this formula as well. Half m AUA square plus half m VUB square, which means your initial kinetic energy is equals to this part here, the final kinetic energy. Okay? But in inelastic conditions, they are not conserved, so there's no formula for us to use, which means some of the kinetic energy is lost. Okay, then for elastic collision, there is actually a velocity formula that you can use, whereby the relative velocity of approach is equals to the relative velocity of separation. So for this type of question, we can actually use this formula here, where u of the first, which is u1 minus u2, is equals to u2 v2 minus v1. Okay, so we can also write it this way if you don't prefer writing A and B. So for elastic, there is three formulas you can use: momentum, kinetic, relative speed of approach, and relative speed of separation. For inelastic, there is only one formula: momentum. Okay. For perfectly inelastic, now what is perfectly inelastic? This is where objects stick together. So because the objects stick together, you realize the mass at the end of the day combines together, but still relating to total momentum is conserved. Therefore, it will be, at the end of the day, they share the same speed, this formula. Okay, so that's the third tip I have. Now, the fourth tip I have is for this part here. It rarely comes out, but it's actually another system that, another collision called the super elastic collision. Super elastic collisions is basically an inelastic collision, but the total kinetic energy is actually different in the sense that the total kinetic energy of the system after the collision is actually greater. It's not lesser, it's greater. Energy is not lost, energy is gained than the total kinetic of the system before the collision. So this kind of energy gain comes in many forms. It can come in the form of potential energy like stored energy, or in the case gravitational, elastic, or chemical, or nuclear. So I give you guys an example. For example, you have a hand grenade. Okay. Now, when you actually have a hand grenade and you have a gun, when you shoot the bullet through the hand grenade, what happens is the hand grenade will actually explode. Now, this causes the total kinetic energy of the system after the collision to be greater, because your hand grenade actually contains chemical energy. Okay, there's explosives and they contain chemical potential energy. Now, then it's triggered when your bullet shoots through the hand grenade, causing it to explode and propelling your bullet even more. So the kinetic energy starts to increase. Okay, so in super elastic collision, momentum and kinetic energy are not conserved, but they become greater after the collision. So this is just one type of collision that is slightly unique. Okay, so let's go through one question here that relates to kinematics and dynamics. First things first, we have a ball that is thrown horizontally from the top of a building as shown here. Now the ball is thrown with a horizontal speed of 8.2 meters per second, and they already say that it's horizontal. So this is u horizontal, correct? Which means that my u vertical, which is my vertical speed, is essentially 0. Then they said at point P, the path of the ball is at a distance x from the building at point P, which is down here, and is moving at an angle of 60 degrees to the horizontal. Air resistance is negligible. This sentence means you can use the equations. Okay? Because if air resistance is not negligible, then you are not able to use the equations anymore. Its acceleration is not constant. Okay, so they say for the ball at P, show that the vertical component of the velocity is this. Now, why is there a vertical component? Because at P here, It's moving downwards like that. This is the velocity. So if you were to actually resolve it, you realize that you can resolve it into vertical velocity and horizontal velocity. So this is VH and this is VV. Okay? So one thing that we can actually look at is when we were to find out what is my vertical component or vertical portion of the velocity, right? I first resolve my velocity in this case here. Now, VH is equals to opposite adjacent, so it will be V cosine 60. And VV here is actually equivalent to V sine 60, right? So what they want us to do is to find V sine 60 here and prove that it is actually equals to 14.2. Now, the thing about projectile motion is that my horizontal velocity don't change, which means to say that my final horizontal velocity is equals to my initial horizontal velocity, and therefore V cosine 60 is equals to 8.2 meters per second. So if I were to find V, this will be 8.2 divided by cosine 60, right? So then to find VV, since I already know what V is, all I got to do is just take 8.2 divided by cosine 60 times sine 60. And this is equals to 8.2 sine 60 over cosine 60. When you guys learned before in math, sine over cosine will give you tangent 60. And if you key into your formula, this is approximately 14.2 per meters per second. Sure. Okay? Okay, now the next part. Once now I know that my vertical velocity here is actually 14.2, I can then move on to the next part. Now the ball, then they say determine the vertical distance through which the ball has fallen. So meaning from here to here. Okay, at point P, what is the vertical distance that the ball has fallen? So to find vertical distance, the first thing I need to do is I need my time, right? Because if I have my vertical velocity and I know the time taken for it to travel from the top to the bottom, then I can find what is my vertical distance by taking speed times time. So how do we first find that? Okay, or let's say if we don't have time, well, the next thing we can do is also to use the equation. Okay, so what's the equation here? What are the main equations that I have to calculate distance? Would be S equals to U T plus half A T squared. Oh, but then again, I don't have the time, so maybe I'll use another formula. V squared equals to U squared plus 2AS. Okay, so then from here, I know that my vertical velocity final wise is 14.2 squared. U is 0 squared because there is no initial vertical velocity. 2, now let's take our downward velocity to downward direction to be positive for all of these questions here. So therefore this would be 9.81 times S. Okay, but my S wise would just be the vertical displacement downward. So from there, SV is equals to 10.3 meters. Okay, up to 360. So since I don't have time, this is the best that I can use to calculate my vertical distance. Clear? Okay, next one. A ball is thrown, same question. Now they say determine the horizontal distance x, which is from here to here. So I already found this distance here to actually be 10.3. I want to find my horizontal distance. So what can I do? I can use time to do it. So first things first, how do I find the time taken? for my ball to travel from here to point P, I can make use of the formula U equals to V equals to U plus AT. And my final velocity is 14.2. My initial vertical velocity is 0. Then this is 9.81 times time. So therefore, my time is 14.2 divided by 0.81, which gives me to be 1.45 seconds. So it takes 1.45 seconds for the ball to move from here to here. So then to find my horizontal distance, all I got to do is just take my initial horizontal velocity times time, since it's not affected by the acceleration. And my initial horizontal velocity is 8.2. My time is 1.45. So therefore, I have 11.9 meters. 360. Okay. So those are the three parts of how we actually use our equations to find my horizontal velocity, vertical component of my velocity. Okay, horizontal velocity, vertical distance, and vertical component of my velocity. So you realize it's really just making use of the equations, asking yourself what you have, and then what you need to find out to actually find the value at the end. Okay. Okay. Now the next one. Continuing the question, the path in ball A with the initial horizontal velocity of 8.2 meters per second is as shown here. Now they want you to sketch the new path of the ball having an initial velocity that is horizontal velocity that is greater than 8.2. So now my ball comes out here with more velocity and there is still negligible air resistance. How would the path be like? So you realize that if there is still negligible air resistance, then there will be a parabolic motion. But because my initial horizontal is actually greater, so what happens is that it will move even further. Understand? Okay. So you'll move even further or even more, and because there is sort of like a greater velocity pushing it forward, and therefore the horizontal displacement here will be greater. The angle will hit at a much acute angle as well. Okay, so for this one here, this will be path G. Now, what happens if it's equal to 8.2 meters per second? So equals to this, but now there is air resistance. So now because there is air resistance, remember my horizontal displacement will be reduced due to the presence of drag force. Okay, so then what happens is that it will be reduced and it will cut short abruptly as well, like that. Okay, so this one will still be A, but it will start off at the same point. So this is what happens if I have air resistance involved in my motion. Okay, then the next one, state and explain in which case, be part 1 or part 2, will the ball reach the bottom of the building first. So for this one, is it greater than 8.2 meters with negligible air resistance to reach the bottom here first, or the one with air resistance? So always remember this is flight going down, right? And if you recall earlier on just now when we revised the part for flight going down, in kinematics, we said that the downward flight will always travel faster than the upward flight. Am I right? Okay. Now, so how do we explain for this one here? Which one actually travels down the faster? It would be part 1. Or the one that takes a longer time to reach the bottom is actually B part 2, if it's equal but with air resistance. Okay, because if let's say my speed is equal, that means in no matter what scenario, I will first have the lowest kinetic energy as compared to this one, because now the velocity is higher, it has higher kinetic energy. So if I have lower kinetic energy, my average velocity will be lower. And since the distance traveled is the same and a lower average velocity, the time taken will therefore be lower as well. Okay. So how we explain here would be something like this. We will say that B part 2 will take a longer time as its kinetic energy is at any point is lower than fast. The average velocity is lower. Okay? Since the vertical distance traveled is the same in both cases, the time taken is lower for case B part 2. B part 1, sorry. Okay? Okay, now the next question, let's take a look at this one here, something to do with dynamics. Now it says, with a suitable definition of the unit of force, meaning we're going to define what does force mean. Newton's second law can be given as the following: force equals to ma. Now remember, this is only if mass is constant, right? Because Newton's second law doesn't say that F equals to ma. It says that F net is equals to the rate of change in momentum with respect to time. Okay, you see, they see body of a constant mass. Using this definition together with Newton's third law, which says that action-reaction pair exist and are equal and opposite, deduced the principle of conservation of momentum. So how do we actually get the principle of conservation of momentum together? So they're actually all related. Okay, how are they related? Now, we learned that in Newton's third law, it's an action-reaction pair kind of law, which means that if any body A exerts a force on body B will exert the equal and opposite force on body A, right? Which means to say that, let's say if I have two bodies, and if body A has a net force on A, then body B will have a net force of negative ma times B, correct? In the negative direction. So we're going to relate this to Newton's net force law, whereby the change in momentum of A is therefore equivalent to negative the change in momentum of B. Can you see that? If you were to relate it like that. Because since net force is equals to change in momentum, that means the change in momentum of A equals to the change in momentum of B. Which means during the same time interval of interaction, whatever momentum that is gained by body A will be the momentum that is lost by body B and vice versa. So that's how we actually show the principle of conservation of momentum. Okay? So if let's say you were to approach this question by just stating the Newton's second law, Newton's third law, and the principle of conservation, and you don't link them together, you will not get the mark because they're not asking you for the definition. They want you to deduce how does it shows that the principle of conservation of momentum arises from. Okay, so how we explain, we will write it this way. From Newton's from Newton's third law, we know that if a body A exerts a force on body B, then body B will exert a force of the same type that is equal in magnitude and opposite in direction of body A. Okay, now why do we have to say that? Because earlier in the first part, they said using the definition together with third law of motion. So we need to actually sort of imply what the third law inside your answer. Okay. Then we continue by saying that hence whatever net force that is acting on A. So in this case here, I'm just going to write it down. The net force acting on A will be equivalent to negative the net force acting on B. Okay. Then just state when M is the mass and A is the acceleration of the body. Okay. Then we continue because they want us to mention Newton's second law. So based on Newton's second law, straight away we can say that the change in momentum of A equals to negative the change in momentum of B. And this means that MA times VA minus UA divided by time is actually equivalent to negative MB times VB minus UB divided by time. Okay? So we can see down here from the, for the same duration of interaction, the gain in momentum of body A is equal to the loss in momentum for body B. So then we conclude, this shows the principle of conservation of momentum. Okay, so this is how we answer this type of question if they want us to use second law and third law. Okay. Okay, so no questions so far. Now, let's take a look at the next one. Practice question 3B, part B here. So now they say, in an experiment, there is an alpha particle of mass m and initial velocity vm, and they are directed head-on towards a heavy nucleus of mass m, and it's stationary. So this is actually a elastic collision, since they already said that there is a head-on collision. The variation with time of the velocity of the alpha particle and the nucleus is as shown. We can see that the alpha particle is actually decreasing in its velocity and changing direction the moment it becomes negative, but the stationary nucleus, initially zero speed, is picking up speed. So write down in terms of m and v naught an expression for the momentum of the nucleus at time t1. So we look at time t1 here, we have the velocity 0.5, right? So using the principle of conservation of momentum, we can say that m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. Okay, so let's take the nucleus here to be m1, and let's take the particle here to be m2. So for m1 wise, we have the mass of the actually let's swap. We take the alpha particle be m1 and the nucleus be m2. So mass of alpha particle is m, so it's m times initial velocity is v naught plus the mass of the heavy stationary is big M here, and the velocity is 0. So then this is equals to m times the final velocity of my alpha particle is actually at t1 is 0.5 v naught. Then plus the momentum of the nucleus, which I don't know and I need to find. Okay, so this is mv naught equals to m 0.5, or I can just write it as 0.5 mv naught plus momentum of nucleus at T1. So if we will just shift things around, we can then get the momentum of nucleus at T1 to be 0.5 mv naught. Okay, so this would be my answer, my final answer. Clear? So just use the momentum of nucleus to help you answer this. Okay, then the next one. In an experiment, an alpha particle of mass m is, okay, so this one we have already read earlier on. So the next thing they say, how we obtain the equation in B part 1. So the only way we do it is by the principle of conservation of linear momentum. So we just got to explain by saying, by the conservation of momentum, the total momentum of the system is conserved, and since there is no external forces acting on the system, therefore the total initial momentum of the system is equals to the total final momentum of the system, okay, at T1. And make sure when you understand the system as a whole, you make sure you include both the alpha particle and the nucleus. Okay, so then we explain by saying, because we know that there is no external force acting on the system, that's why I can use my equation straight away. Okay, now then the next part, it says, the alpha particle is closest to the nucleus at time t equals to 2. So if we look at the back arrow diagram, at time t equals to 2 here, this is where they are the closest to each other. Now, the velocity of the alpha particle at this time here would be v. Okay, so I don't know what velocity it is. I just know that for the alpha particle, if I were to draw a horizontal line here, this is actually just a v. So determine what this velocity v of the alpha particle is in terms of that. So same thing, what we're going to do is we're going to use by the conservation of linear momentum, since there is still no external force acting on it. Okay, so by conservation of momentum, you can see that the total initial momentum is equals to the total final momentum of the system, right, at T2. So then at T2, my initial momentum here, m1u1 plus m2u2 equals to m1v1 plus m2v2. Remember, my m is my alpha nucleus, so it's m mass times my velocity, which is v naught, plus, and this is capital M, but my initial velocity for my nucleus is 0. Okay, then for my alpha particle is small m. Now my velocity here will be a small v, right? Then plus. So what is my velocity for, in this case here, for my nucleus? You realize it is also v. Can you see that? Since they share the same velocity and they are closest to each other, that's what they say at T2. So it's capital M times v. So from there, I have mv naught equals to mv plus big M v. If I were to factorize out my v here, I'll get m plus big M. So therefore, my velocity is mv naught divided by small m plus big capital M. Okay, so that's how we get this part here. Okay? Okay, now the next one. They say in a separate experiment, an alpha particle, so now the system is separated. I have an alpha particle that collides head-on with a stationary nitrogen-14 atom. So this is a elastic collision, and straight away elastic, momentum conserved, right? Kinetic energy is also conserved, and you can use the speed of approach equation, the speed equation. Okay, so first things first, they say the nitrogen atom moves off in the same direction, so the sign don't change as the approach. Oh, sorry, the nitrogen atom moves in the same direction as the alpha particle now, but now the speed is 0.005 c. The c is the speed of light. Discuss quantitatively, meaning use calculation, whether the interaction is elastic in nature if the initial speed of alpha particles is 0.02 c. So if it is elastic, then it needs to fulfill all these conditions, correct? So first things first, what we're going to do is obviously using the conservation of linear momentum. So for this case here, by the conservation of linear momentum, you can see that m1u1 plus m2u2 is equals to m1v1 plus m2v2. Let's make the alpha particle m1. Let's make the nitrogen atom m2. So for this one here, alpha particle. Now, what is alpha particle? You have to remember that alpha particle is actually your helium nucleus, not the atom, just the nucleus alone, which means that it is actually mass 4 He with a charge of +2. So the mass of your helium nucleus therefore would be 4 units, and then my initial velocity with a speed of 0.02 c, right? Then plus, now my nitrogen particle has a mass of 14 units, but its initial velocity is stationary, so therefore it's 0. Then this will be equals to 4u. Now what's my final velocity of my alpha particle? I wouldn't know, so I'm going to put it as v1 first. Okay, then in this case here, I'm going to add the mass of my nitrogen nucleus, and now the speed is 0.005 c, moving in the same direction as my alpha particle, so there is no change in sign. So then from here, I can calculate my final speed of my alpha particle to be 0.0025 c. So this is my first value. And then if it's elastic, now I can use the second equation, which is the speed equation. So which means the relative speed of approach equals to my relative speed of separation. Okay, if they are elastic. So I need to calculate these two values separately. So what is my relative speed of approach? Now my relative speed of approach is equals to u1 minus u2, right? So this is equals to u1 minus u2, and u1 is equals to 0.02 c, u2 is 0, so this means 0.02 c. Then what's my relative speed of separation? Relative speed of separation is equals to v2 minus v1. So this will give me 0.005 c minus 0.0025 c, which gives me 0.0025 c. Then you realize this is not the same. And if they are not the same, therefore it is not elastic. So it's just a head-on collision. Understand? Okay. Can? All right. So that is for this part. Now, dynamics and kinematics. Now, the next topic would be for forces. So when we talk about forces, so first things first, the first tip I can give you guys is mainly on the formulas part. So in forces, there are just many different types of formulas that you need to remember, especially the ones for Hooke's law, F equals to kx, pressure. If let's say it is just pressure of a fluid is rho gh, but if it's an open top whereby you have an open container and then there is exposed surface to the surrounding, then don't forget to add your atmospheric pressure. Next, we also talk about arc thrust, whereby arc thrust is also equivalent to density V times gravitational force, whereby it is the density of the fluid times the velocity of the fluid that is being displaced times the gravitational force. I mean the gravitational field strength. Okay. Then we also went through, you also had the concept of principle of flotation, whereby it says that if a body is partially immersed, means not fully submerged, partially immersed, the weight of the floating body will be equals to the weight of the fluid displaced. Okay, so this is important. You also learned the principle of moment, whereby conservation of moment, whereby in this case here, moment is force times the perpendicular distance of the force with respect to the direction of the line of action about a pivot. And then we can also use that concept to find the torque of a couple, whereby if let's say I have two forces that causes an object to undergo rotational movement, then to find the torque of the couple, I will just take the force, one of the force, don't have to take both of them, times the distance between them. So that's the thing that you need to take note of. Understand? Okay, and one of the force. Don't have to times 2. Clear? Okay, then because it's forces, it's also related somehow to dynamics, which means that you will need to actually draw your free body diagram, find out where your forces are, what is the net force, so on and so forth. Okay? Okay. Now, so then the second tip, equivalence of 3 forces. So sometimes they may give you a diagram where there is more than 1 forces present. In that case, if they say that the system is in equilibrium, you need to make sure that all the forces balance each other. And how do I know that? That is whereby I need to make sure that the line of action for all 3 forces intersect at a single point. And that's when they are actually equilibrium with each other. For example, I give you a diagram here. I have a bar and there is a string pulling on it. So naturally, we know that the string possesses tension and is acting upward. Okay? There is a force F in this direction, and lastly, there is a weight force acting at the bottom. So how is it that they are actually balanced with each other? That means I need to change my variation or my value of these 3 such that they fit into a system whereby they all coincide with each other like that. You understand? Which means to say that the length of this part here, okay, will give rise to the magnitude of my tension. The length of this distance here will give rise to the magnitude of my weight. And lastly, the length of this distance here will give rise to the magnitude of my force, so that these 3 forces in a way balances each other by intersecting at a point. Okay? If I have them in different directions like that, they don't intersect, then this is not balanced. So this case here, the rod or the bar is not in equilibrium. Okay? Okay, so that's one tip that I can give you guys. Then forces being forces for this type of question, we will always have to draw our free body diagram and label where our forces is. Okay, so if we take a look at this question now, it says, I have a 3.8 kg block on the plane that is inclined at 15 degrees and has an initial speed of 5.0 meters per second. So when a horizontal force F of a magnitude 25 is acted on E, it is shown here. So this force here is equals to 25 Newton. Okay, there's an initial velocity of speed of 5.0 meters per second, and it's 3.8 kg. Determine the normal contact force exerted by the plane on the block, which means to say, always remember, normal contact force is directly proportional to your surface. This is your surface, understand? So if it's directly proportional, sorry, not direct, perpendicular, then this would be your normal contact force here. Understand? So what we are trying to find out is actually the normal contact force acting upward. Now, since it says that a block is inclined, and in this case here it is not moving, we say that the net force is equals to 0, right? It's just stuck there. So then my main job now is to find out what my net force is. Okay, so how am I going to do that? I have a horizontal force here. The only way I can actually do it is if I were to resolve all my forces. Okay, so before we move on, the next thing you need to draw is the weight of the box. So if I were to draw the weight downwards, because weight is always acting downwards, this is 3.8 G. Okay, so what are we going to do now? We're actually going to resolve my force. So you realize my weight can be resolved downward like that, and then I have a horizontal force like that. Okay, so 15 degrees is here. So in this case here, opposite, adjacent, this will be weight cosine 15, and this will be weight sine 15. Next, on top of that, I would actually need to have our resolve my force here. So how am I going to resolve my force? Now, I need my force to have an upward force, and then there is also a horizontal force like that. So if I use another color pen to draw, you can see that there will be an upward force here, and then there will be a horizontal force here. Can you see that? Okay, so saying this is 15 degrees, so this will be opposite, so F sine theta, or F sine 15, and then this will be F cosine 15. Okay, so now, what is this F net that I'm talking about? Because your block is lying on the surface, it's not moving down through the surface, or it's not floating up from the surface. So in this case here, the forces in the upward direction balances the forces in the downward direction. Can you see that? Okay. The horizontal forces, we are not interested in it yet because we are not talking about the motion left or right. So in that case here, if my net force is 0, and then what is my net force? You can see that my normal contact force, which is this direction, plus my F sine theta, F sine 15, is actually equals to my weight, which is the only force acting down here, W cosine 15. Okay, so let's take the upwards here to be positive, and the right side, left side, since it's moving left side to be negative, positive as well. So in that case, my N is equals to W cosine 15 minus force sine 15. Okay, W cosine 15 minus force sine 15. Then this would be, now my W is actually 3.8 kg times negative 9.81. Why negative? Because I took upwards to be positive. And since G is acting downwards, so therefore I have to put in a negative 9.81 cosine 15. Okay, then this is equivalent to minus. Now, in this case here, my force is 25 sine 15. So then when we calculate, the value we get here would actually be approximately negative 42 Newton. So since we only want the magnitude, therefore my normal contact force is just equivalent to 42 Newton. That's all. Okay. Okay, next. Now, they say the coefficient of kinetic friction mu is 0.4, and the kinetic friction formula is related to the normal contact force formula by this, F equals to mu n. So they say calculate the magnitude of acceleration of the block. Now, I want the magnitude of acceleration, which means I will need the net force, right? And in this case here, the net force by Newton's second law is equals to ma. So then what is my normal contact force? Since this is talking about kinetic friction, you can see that my block is trying to move forward up like that, correct? Okay, and in order for my block to actually, oh wait guys, there's something that I want to change. Okay, my forces for this one, right, I cannot draw it like that. Why? Because you realize my force is moving in this direction for 25, which means to say that this, okay, let me redraw it. We have W sine 15 here. Okay, now for this force, because it's moving in this direction, so in order for you to have an upward force and a downward force, and to produce a horizontal direction like that, then my forces need to go in such a manner. My downward force here, and my horizontal force here. Do you understand? Okay, because my force is moving in this direction instead. So this changes a little bit of things. This is 15 degrees. So this is still F sine 15. And this is F cosine 15. Okay, so you need to look at the direction of the force to determine where you draw your resultant force. So because of that, the net force is equal to 0. That means in this case here, we need to swap things a little bit. My normal contact force, which is up, is equivalent to the sum of these two normal contact force. Yeah, then it makes more sense. Okay. Then from here, we add them up together. Then this would be equivalent to 3.8 times 9.81 times cosine 15 plus 25 sine 15. And this should just give you 42 newtons. Okay? Okay, so once we get this diagram, then we can answer this question here. So they said that F net is equals to ma, and my F net I'm talking about now because it's acceleration, it's my movement horizontally. So you can see that since it's moving up here, means that there is actually a net force in this direction, right? Since it's moving up. So how is there a net force in this direction? There is a horizontal component here and a backward horizontal component here. Okay, and don't forget, because there is actually a friction present, so what happens is I have a friction, kinetic friction that we see earlier on, acting downwards because my motion is upwards. Okay, so if I were to combine everything together, I can therefore say that my F net is F cosine 15 minus my small f minus my W sine 15. Okay, okay. Okay, so we can say here that F cosine 15 minus my kinetic friction minus my weight sine 15 is equals to NA. Then all I got to do is just put in the values. For this one here, I want to find A. So I'll take A is equals to F cosine 15 minus my kinetic friction divided by my mass of the block. Okay. So this will be equivalent to, this is 25 cosine 15 minus, now, what is my mu here? They give it to me as 0.4, and my normal contact force I found earlier on to be 42. Then this is 3.8 times 9.81 times sine 15, then divide by the mass of the block, which is 3.8. Okay, then from here, I will get the value to be 0.66 meters per second squared. So this is my acceleration for part 1. Okay. Then the next part, determine the distance traveled by the block before it comes to a rest. So before the thing comes to a rest, what is the distance traveled by the block? So for here, to calculate the distance, all we got to use is just use since we have the initial velocity and the final velocity as well as the acceleration, this is not 9.81. All I got to do is just substitute in. Therefore, the distance traveled will be equals to, just manipulate the equation a little bit, then you will get negative 5.0 square over 2 times my acceleration, negative 0.66. Because if you calculate this, you will get the value of negative 0.66. But because the initial question only wants magnitude, so I didn't include that. Therefore, the distance traveled is 19 meters. Okay? Okay, now the next part, it says, static friction is the force that acts on an object when it's at rest. Okay, and it must be overcome before the object can start moving. Now, considering that the maximum possible static friction between the object and the plane is equal to the value of the kinetic friction, so now they're saying that the static friction is the same as kinetic friction, state whether the block will slide down the plane after coming to rest if the force continues to act on the block. So to do this, what we need to do is we actually need to find a component that is parallel to the block, meaning to say we have to find this component of the block. So if I were to put this one, okay. So let me just pin the image here so you guys can see better. Okay. What we are looking for is actually the force. You see, if you realize, we want to look at the friction, which is this part here, static friction, and therefore we want to look at the component that is horizontal here. Okay, so first things first, component of force parallel to plane will be equals to F cosine 15. And if I sub in the value of F, 25 cosine 15, I will get 24 Newton. And if I look at my component of my weight here, okay, so component of weight, W, parallel to plane, I will get W sine 15, which is equals to 3.8 times 9.81 sine 15. And I get 9.6 Newton. So you realize one is 24, one is 9.6. Then don't forget, we have our kinetic friction as well, mu n, which is 0.4. And then my Newton, normal contact force is 42. So it's 17 Newton. Okay. So if we were to actually calculate them all together, by right, my net force should be equals to 0. If let's say it does not slide down, okay, that means my equilibrium force balance is 0. So what happens here is you realize that F cosine 15, which is this force here, 24, is equals to my W sine 15 plus my frictional force. In this case here is 9.6 plus 17 Newton. And if I add 9.6 plus 17 Newton, I will actually get 26.6 Newton, and it's not equals to 24. Can you see that? Okay, so what happens is, since it's not equals to 24, we will say, therefore, the block remains at rest, because it's not enough to actually cause the block to slide down. Okay? Okay? So that's for question 4b. Now, question 5, I will not be going through, but I'll upload the answer since the time is up. Okay, but just take a look at question 5 and try your own first before you look at the answers for question 5. Now, so just very quickly to summarize, whatever I have taught you guys today is all from our curated notes. So if you want, you can also go and purchase the curated notes from the website. And then after that, look through all the examples inside. We have a lot of examples, tips, answering techniques as well. And if you realize you need more help, we have group tuitions and crash courses to help you. Now pay attention to the crash courses, because it's actually pretty important if you want to have like a full-fledged lesson on what you are going to be tested on, as well as a quick revision. Okay, so this is just the sign up for the group tuition as well as the crash courses. Okay, so I will send the Telegram group chat later, so you guys can actually look at what you need to learn. We'll be going through during the crash course during the June holidays as well. Then since you guys are J1, most likely you just need to attend the first module. Okay, it's like module 2 and module 3 is mainly for J2s. Okay? Okay. So that's all for today. I hope you guys actually learned something. Okay, so all the best for your block test or your mid-year revision that is coming up, most likely after the June holidays. Okay? Okay, so if there's no question, you guys can leave the chat. Bye-bye. Thank you, no problem.